Ready, Peter?
Yes.
All right. Well, it is a great pleasure to have Peter Fellow here, who will tell us about things about the values taken by STI. Slice.
Yes.
Awesome. Thank you.
Thank you so much for having me. And I'm really sorry to not be there in person. Some people of you in that room, I got the chance to finally see again in the US a few weeks ago, but I really wish I were there in person, but I'm not. This is how it is. I'm teaching. So in the morning I teach, and then in the evening I join you guys. This is about on the values taken by the slice-torus invariants, and the talk has a plan. Well, the talk is also with collaborators, Lewark and Lobb, and the talk has a plan. Namely, I'll briefly talk about Knots, concordance, and the local Thom conjecture, and then I'll dive in and tell you what slice-torus invariants are. I want to tell you why one should or could contemplate studying them. And I'm going to tell you what they do for you. And then I'm going to give you what's the main result of this talk, but it's certainly not the main result of the subject or the reason why we started studying. And this is more related to what's known or what we call squeeze knots. Okay, that's sorry for the screaming. My stuff is jumping around. Ooh, I'm back. Squeeze knots, here they are, and Andrew is going to talk more about them. And this talk is completely independent of his, but for a little bit more background on why what I do here could be considered important, I refer to his talk. And then finally, I'm going to give you, so my plan is to tell you a little bit how slice-torus invariants show up in knot homologies, but then there will be a construction and a proof of a result, where actually there's no knot homology. So we will have a construction from nothing. And then there's questions, and the way the talk is supposed to develop is I will always on the left-hand side actually write, right now not, but in a second when I go to the first slide, and on the right-hand side, there will always be additional information that I will point to at a given moment. And so before I actually start my talk, I'm going to do a complete spoiler of anything that is happening in this talk. And if you're an expert, this might maybe be enough to tell you everything that is in this talk. And then I apologize, but at least you know ahead of time and can run away. My point will be, I will tell you what slice-torus invariants are. Just a knot invariant, real valued. It's additive under connected sum. It's a lower bound for the 4 genus, and it is equal to the 4 genus of Taurus knots on positive Taurus knots. By the way, this is going to be very fast. If instead, while I go through this, you don't understand everything, great, look forward to the talk that is about to come. Why could you study these gadgets? Well, you can reprove the local Thom conjecture, and maybe you can use them to produce summons in the so-called smooth concordance group. That's a good reason. Where can you find them? I talk about this because, with one famous exception, all slice-torus invariants that were kind of built come out of quantum topology. And what do they do for you? They give you, kind of by definition, a lower bound for the 4 genus, but we will look a little bit more closely and go to the notion of stable 4 genus. It also gives you a lower bound for this. And then I will give you a somewhat horrid defined quantity, and this blue thing. That will also be a lower bound for. And I will try to argue why you should care about this quantity. Right now, you only need to know this is purely topological. It's only in terms of the 4 genus. And the result I'm actually going to prove is indeed, if you want to know what values slice-torus invariant takes. So this is the set of, for a given knot, real numbers that you get when you have a slice-torus invariant. I'm going to teach you it's a closed interval where the 2 corner points are this quantity I give you above. And let me just tell you, before we started this investigation, if you had even tried to tell me I need to prove that this set is connected, or let's say compact, I would not have known how to do this. It's kind of fun that it works out. Although once you will see the proof, it will surprise you so much. And then I will give you some connection to squeezedness. I'm not defining squeezedness right now. I just want to say a knot is squeezed. This includes lots of examples of your favorite families of knots: positive, alternating, homogeneous, any connect sum, negative, quasi-positive, quasi-negative. All of these are squeezed. And in this case, all my slice-torus invariants are pretty boring. And this is actually kind of a philosophy of the talk, or this squeezedness. If you have interesting invariants that you cooked up with quantum topology, probably don't try them on squeezed knots, because they will just be boring on squeezed knots. This is something I can make more precise. And then finally, in terms of building, I said I need nothing. That was a slight lie. I will be able to build slice-torus invariants just from the statement of the local Thom conjecture, which says something about the 4 genus of torus knots, and using the Hahn-Banach theorem. So when I say I need nothing, I really mean I need nothing from this millennium. So I don't need any knot homology theories. Any questions about this complete spoiler of the talk? And if not, I would start the proper talk of the part of the talk. And also, if you have questions, I don't think I see what's going on in the chat. If you have questions, please speak up. And if you see somebody else has questions in the chat, maybe shout at me to look at the chat. That would be very kind. Well, depends on the level of shouting you do.
Maybe a question? A question, perhaps?
A question in the back.
Yeah. Can I be clearly heard? Speak louder. Oh, can you hear me, Peter? I have a question.
Yes, now I can hear you now that you're being loud. Yes.
Okay. So I noticed in your definition of slice-torus invariants, you only enforce a value of the invariant on the PP plus 1 torus knots. Is that sufficient by some like short cover argument to get sharp?
Yes. It's the same as if you have this is equivalent to having it on all positive torus knots. It's equivalent to having equal to the 4 genus on all quasi-positive knots, on all positive knots. It's all equivalent. Okay, it's just, that's the quickest way to state it.
Yeah, so you can do that argument for any concordance homomorphism?
Yes.
Yeah.
No, just as soon, if you have a concordance homomorphism which has these properties, then it's true on all the other ones by some quick cobordisms to other torus knots. Somehow, any connected sum of torus knots has a quick cobordism to a really large torus knot of this form. That's kind of the proof, and then everything else follows. If you know how to prove the slice-Benka inequality, this is enough to prove it, and then you have equality on all positive braids and stuff like this.
Perfect.
You're welcome. Okay, let's start the talk. My talk, let me really set up notation, is about knots. And my favorite knot is, of course, I denote them by K. My favorite one is the unknot, will be denoted by U. We maybe all love the trefoil, and for me, knots are really smooth, embedded, connected, one submanifolds, oriented, non-empty of S3. I actually don't draw more. And my favorite set of knots are so-called torus knots. Just to fix notations, to the left, I drew you an example of 3, 4. But let me actually recall that the quickest way to say what a torus knot is you pick complex numbers, x and y, and you look at y to the p minus x to the q, and you set that equal to 0. So you have an algebraic curve in C2. And maybe you want p and q in Z co-prime. You can fight with me over what happens if you're 0, because it doesn't seem well defined, but don't worry, just ignore these points. Okay, these are torus knots. Explicitly, they're called torus knots because you can draw them in the most standard S1 cross S1 in S3. I want to think about concordance, which I denote by K is equivalent to J if K is concordant to J. And let me just warn you, all my things, there's an N missing, all my manifolds are oriented and smooth. Here's a picture of what concordance means. Concordance means you have an embedded smooth analysis in S3 cross 0, 1, such that on one side you get your one knot K, and on the other side you get your knot J. You have to be careful about what happens with orientation. Concordance allows you to build the so-called concordance group. If you denote all knots to isotopy by, let's say, knots, and you divide out concordance, you are no longer just a monoid, you're a group, and the group structure is given by connected sum. And there's actually an inverse. It's written as minus K. If you take the mirror and then the reverse of your knot, so reverse means switching orientation, mirror means actually applying an orientation reversal diffeomorphism, this gives you the inverse. So the class of this is the inverse. And let me also just tell you that there's a nice metric on the concordance group, and the metric is given by, if I have two classes, K and J, I just look at this so-called cobordism distance, K, J. There are two definitions for the cobordism distance. I could either go back to my definition of concordance and replace annulus by any genus surface and minimize over all possible genera, but I'll give you a quicker version. I can define concordance by saying K connect sum minus J slice for genus is equal to 0, where the for genus by definition is the smallest genus among oriented surfaces in the for ball with boundary you're not. And then with this trick, I can say that this is a quick and dirty definition of the cobordism distance. It's actually a metric. It satisfies the triangle inequality. Okay, why? So why do you want to study? I feel like I'm the first person to talk about this gadget, so maybe I'm responsible to briefly talk about why should we study concordance, the concordance group. Some people will say, oh, it's per se an interesting group. It kind of reflects smooth topology phenomenon that you also that contrast with locally flat topology phenomenon. But let me give you two extrinsic reasons that I find worth mentioning. The first thing I wanted to say is the question of whether a knot is slice, aka whether a knot is concordant to the unknot, you can think of as the most basic obstruction to surgery working. Let me say it this way: surgery obstruction question. And now this doesn't say anything, so let me explain what I mean by this. So here's a question you could ask in any dimension. When you have an embedding of S1, I'm still thinking of smooth, and I'm going to call my embedding K, like for knot, into the boundary of a four manifold. And the of any n manifold, actually. And your boundary injects into your manifold. Then S1 is the boundary of everybody's favorite two manifold, the disk. And you can ask the fundamental question, under what conditions can you find an embedding here? When does there exist an embedding phi? That's a fundamental question you can ask. And let me tell you, well, if you go through here, you will get you will see that the boundary has to be null homotopic. So a necessary condition for sure is the composition of these two maps has to be null homotopic. So homotopic to a constant thing. But here's the point. This is also sufficient in almost all dimensions. If the dimension of your smooth four manifold is not equal to 4, then that's an if and only if. And in all dimensions except 3, this follows either by the classification of surfaces or by general position. And in dimension 3, there's something to prove, and this is known as Din's lemma. But I like to put it that way to you because it actually turns out that whenever you can answer this question, when there's only this homotopic obstruction, that is what you need to do surgery theory. And this is why low-dimensional topology is a bit weird in comparison to high-dimensional topology. So, okay, that's an important basic question. When can you extend a map from this embedding from the circle to an embedding of the disk? And my point is, what's the most local, simple thing you can do? Well, clearly the problem is only interesting in dimension 4. What's your favorite 4 manifold with boundary? It's B4. What's your favorite, well, what's the boundary of this? It's S3. And now what's the point? What does it mean for an embedding of the circle in S3 to bound a disk? That's exactly sliceness. So the answer to this most basic surgery obstruction question is yes, if and only if K is slice. Or put in different way, K is concordant with the unknot. This is actually not relevant for the rest of the talk, but I just felt like reminding us all that there's an honest, natural reason why we should study sliceness this way. Here's another, I find natural reasons and inspiring to study all of this. Whenever I have knots, or whenever we have knots, by taking some p-fold branch cover, for example, a double cover, you can produce a rational homology 3-sphere. And the type of things that might be interesting is if instead you have an element in the smooth concordance group C, you can go find an element in rational homology 3 spheres modulo some relation. For example, the relation of rational homology cobordism. So that for me is another reason to think we should study C. So I hope that's enough of reason for you to care about C. And now I'm going to state the local Thom conjecture. And to satisfy the back row, let me actually give you the more complete statement. Now, if PQ are any co-prime integers, you know what the 4 genus is. And the 4 genus of this thing is absolute value P minus 1 times absolute value Q minus 1 halves. So that's the statement of the local Thom conjecture. But I do think it does it a little bit of a disservice to just write it like this. It says something much more fundamental about complex surfaces being minimizing. So I'll just remind you what Kronheimer-Moravka actually proved, and then the local Thom conjecture is a corollary. Although these days, in particular in your state, we also know the converse. If you have a homology class given by a smooth surface, sigma, that as a homology class is d times the CP1 in CP2, second homology class with set integer coefficients, it turns out that the genus of this smooth surface is always bigger or equal than the genus of a smooth complex curve of degree d. So complex curve representative of this homology thing. And there's an explicit formula that you can figure out by hand. And it involves something which looks a lot like this. And then the local Thom conjecture is a consequence. I won't be needing the Thom conjecture or this Kronheimer-Moravka statement. I just need, there is the 4 genus of Taurus knots, and it has an explicit value. Questions about my setup of knots and the statement of the local Thom conjecture? If not, I go to my slice-torus invariants. So, as we discussed earlier, slice-torus invariants are real. Oh. So my Zoom panel is in the way of my writing, if people are wondering what's going on over at me. Okay, it's a real valued knot invariant. I want it to be additive, so that means if I have a connected sum, I wish this to be the sum of the values, such that additionally, I have the 2 properties that I mentioned earlier. It's a lower bound for the fourth genus. For all knots. And on Taurus knots, we have equality, and that is on positive Taurus knots. P minus 1, Q minus 1 halves for P and Q positive and co-prime. So far, so great. Let me give you, well, let me give you a first example. The first example is the tau invariant by Ozsváth-Szabó. And this comes out of Heegard-Fleur. And maybe here's a natural point to stop and briefly talk about the history of slice-torus invariants. So Ozsváth-Szabó defined tau, but then arguably Livingston was the first to implicitly define slice-torus invariants because he wrote this paper calculation of tau for some knots, and he just showed only using these formal properties that I have here, you can do lots of calculations. So arguably Livingston is the first to define it, but since there was only one, there was no point in giving it a name. And my co-author, Lucas Lewark, is, I think, the one who introduced the term slice-torus invariants, because he was studying quantum invariants. And that's, of course, the point. All the other such invariants we know about are quantum from the quantum world. So there's the Rasmussen invariant from Kovanov homology. To be more precise, from Lee's perturbation of Kovanov homology. And then Andrew Lobb generalized that and independently Wu generalized this for other SLN homologies. Again, you need to take a perturbation. In this case, the perturbation is due to Gornick. And actually, Lobb and Lewark went on and produced variants of these SLN things. They choose some potential, some polynomial. That's due to Lewark, Lobb. And again, given the title of this conference, I want to stress, except maybe the odd and first tau, the only invariants we are aware of that are slice-torus come from quantum. Feel free to correct me if you think you have another one. And maybe, okay, there's maybe a choice of field involved that might sometimes give different things, but otherwise I think that's all the slice-torus invariants we are aware of. Why would you want to study slice-torus invariants? Let me, now that we have some examples, let me remind you of a result by Hom. And it's appropriate for the state you are in, if not the city. And she proved that this huge, actually abelian group, has a Z infinity summand. So it's isomorphic to this. And this per se is not yet that interesting because let's say there's some group homomorphism to a group of this form. But what is interesting, I told you earlier, we really care about the smooth concordance group in connection with what happens with the topological concordance group. And what she showed is this summand is actually a subset of the topologically slice subgroup, meaning the set of classes where K satisfies the topological for genus of K is 0. I'm not defining it if you don't know what's up here, but I'm just saying these interesting questions are: when can you find interesting summons in the concordance group. And so what's my point? My point here is, first of all, you may wonder, can you use, because Jen did not use directly slice-torus invariants to produce such summons. Can you use slice-torus invariants to reproof this type of results? And more generally, can you use slice-torus invariants to find interesting summons and subgroups? And this actually makes sense, and I'm going to give you quickly over here some reasoning. Whenever you want to find infinite cyclic subgroups, summons even in some group, abelian group, I don't even need this to be C. This just works in general. One way is to find many group homomorphisms. So whenever you find a group homomorphism, let's say to Z, which on given element is 1, and on all other elements, let's say there are countably many of them, is 0, then the span of these elements are an infinite summoned. And if you could do this with slice-torus invariants, you would actually reproof Chen Hom's result and actually something stronger. So you can wonder, can you do it? That's my motivation for why one might study slice-torus invariants if one is primarily interested in the concordance group. Questions about this page? If not, I want to tell you what slice-torus invariants are topologically useful for. So here's the point. Kind of by definition, those things give you a lower bound on the 4 genus. You can say it's an obstruction to sliceness, which gives you some quantitative information. But if you dig a little bit more, you notice this is not optimal. Because of additivity, you immediately see that if you instead take n times a knot, do the 4 genus, and divide by n, you get the same thing, just because it's additive. This is my notation for n times self-connect summing a knot k. Wait. If I do the invariant, but then that's a lower bound for this quantity, which is known as the stable 4 genus. So you shouldn't really think of a slice-torus invariant as a lower bound for the genus. You should think of it as a lower bound for the stable 4 genus. And let me give you a little bit on the stable 4 genus, explicitly studied by Livingston with this definition. It's less than the 4 genus. A priori, it's only a real number, and we know nothing about the stable 4 genus. Let me tell you, we don't know whether it's always a rational number. We know Livingston constructed a family of knots such that the stable 4 genus is closer and closer to 1/2, but we do not know the exact values. We just know Z can show up, and it's not everything. There are some other values, but I couldn't tell you whether there's a single value that is not an integer that is rational. I couldn't tell you whether there's a single value that is not an integer that is irrational. Oh, well, there I didn't have to say it. So this is really a bad understood quantity. That being said, this is still not optimal. This is not really what the slice-torus invariants are a lower bound for. And so now I'm going to tell you what's really up. And here is a small calculation. So slice-torus invariants are additive. So I might as well add and then again subtract some knot. And And philosophically, instead of doing it with these particular knots, you could take any, say, positive knot, positive braid knot, just complicated enough ones. I'm doing it very explicitly. And okay, I know that these slice-torus invariants are lower bounds for the 4 genus. So here is the 4 genus. And then I know on Taurus knots, they are actually equal to the 4 genus and equal to the stable 4 genus. So this is the same as TP plus 1. Okay. So this is kind of a version of the stable 4 genus, except I kind of looked, if you think of this as a semi-norm, I don't know whether you like this. If you tensor the smooth concordance group with R, the stable 4 genus actually turns into a semi-norm. So if you think about it like this, you kind of can look at the weird triangle inequality quantity that somehow measures distance to a certain positive knot. I don't know whether that tickles your intuition. Let me just give this number a name. And let me give you a definition. Here's the definition. Rather than looking at just the stable 4 genus, I end up looking at this limit. And this limit actually exists. This is well defined. Since, well, actually the very first element, when P is 1, this is an unknot, so nothing happens. So this is just T1. And then it turns out this is this decreasing sequence of real numbers. I don't know what they are, but they're certainly all bounded below by minus the stable 4 genus of K. If you don't believe me, but if you believe me that this is kind of a semi-norm, triangle inequalities, there's stuff like all these are smaller than the 4 genus, but they're also, it's the wrong way around. They're also bigger than minus the 4 genus. Triangle inequality. So if a decreasing bounded sequence, it has a limit. Great. And yeah, this is a quantity. Again, rather than doing it the way I did it, you could say, I don't take these particular positive knots. I take all quasi-positive knots rather than these and build the infimum of the quantity I wrote here. I wrote here. And the same would come out. So this looks a little bit special, but it's actually, it just measures some distance to the set of positive knots in some sense. Okay, I wouldn't have come up with this quantity if I didn't have the following theorem. The point is, if you want to know, and that's the title of the talk, it's also the title of the paper if you want to Google it, what's the value slice-torus knots can take? It's exactly the closed interval that you can define using this L. And for convenience, I brought L to the next page. And I'm going to explain why this is true, and it's actually easy. There's no honest knot theory involved. Or I'm going to give you intuition why it should be true. But I also promised you to tell you why you would ever come up with a theorem of that kind. And for this, I'm just going to define for you the notion of squeezedness. Actually, before I do, let's again go over here to the examples. Positive, negative, alternating, homogeneous, quasi-positive, quasi-negative knots are all squeezed. So squeezed knots really include lots of families of knots you might like. And when we are a bit farther, I'll say something more philosophical. So definition, a knot is squeezed one possible definition is if there exists a natural number such that the distance between positive torus knot p plus 1 and the negative torus knot, which is minus of this, but I can write it in here, is equal to the distance between this positive knot to k plus distance between this negative knot to k. That's my definition of squeezedness. I'll try to give you an intuition over here. It really means there's some positive knot, and it turns out I could have said positive knot rather than these specific torus knots, and there's some negative torus knot such that k lies on a kind of geodesic, on a shortest path between the positive and the negative. In that sense, squeezed. Somehow a knot is squeezed if it fits between the positive and the negative knots in the fastest possible way, where fast is defined using concordance. Again, just this definition might not look so appealing, but recall all your favorite knots are actually squeezed. And let me give you another statement, which is, I'm going to call it an observation, but you can also think of it as an obstruction. If K is squeezed, then all slice-torus invariants agree. In particular, this set over here, which I maybe for future notice just call I of K. This set is just 1 point. So all slice-torus invariants have the same value. For example, Rasmussen S invariant halves. It's one way to say it for all slice-torus invariants. And I'm actually going to prove that for you, and it will be just a little trick with triangle inequalities. But let me just in words also mention, oh, this wasn't supposed to be here. Let me also mention that there are refinements of slice-torus invariants, such as refinements of the S invariant by Lipschitz-Sarkar, by Dirk Schütz is another one. There's also a refinement by Sarkar, Scaduto, Stoffregen. And all of these invariants are equally simple in a way on squeezed knots. So what I'm trying to tell you is, if you ever invent a new quantum invariant, you should know about squeezed knots, and be it just for the reason that you should try to avoid them. If you have a new invariant and you're trying to show it's very subtle, squeezed knots will just kill you. And I can tell you in the knot table of 10 crossing knots, all but 5 are squeezed, and they will never behave interestingly on slice-torus invariants and certain quantum invariants. So I feel like we should all know about squeezed knots for that reason. And this is how it came about for Andrew and Lucas, my co-conspirators. They're inventing these things, and now they know classes of knots on which not to test things. Let me also mention that now I said a lot of examples of squeezed knots. Here's an example of a non-squeezed knot. If you take the knot 10, 125, I drew you a nice little picture over here. You might notice that it's more than 10 crossings, but actually, no, it's exactly 10 crossings. It's a pretzel knot, a nice one. One can calculate using SLN S invariants that this interval for K is yay big. So in particular, you can't be squeezed. So they take different values. And actually, I can give you an actual slice-torus invariant that comes out of quantum that takes on exactly 0. Or well, Lucas can't. That's really his result. But since we know it's a closed interval, that's enough to know it gets very small. So there are knots where this interval shows up as a set of values that slice-torus knots can take on. And so with a cheap trick, you can look at this knot, where for any a less than b integer, you build k times the connected sum here, and then you add on some trefoils. And if you do this, you find that at least all intervals closed, bounded, where the boundary points are integers, show up as values for slice-torus invariants. And we don't know whether there are any others. So that's one of the questions I have at the end. Is this all the values that slice-torus invariants can take on a given knot, or can it be different things? We don't know. Okay, I wanted to give you a quick proof of this observation. And this is really one of these proofs, which is just a little triangle inequality move around. Let me give two names to quantities. If I evaluate a given slice-torus invariant on a given torus knot, and then on my knot that I start with, and I'm going to call that equation 1, then this is a lower bound for, you can connect some together for the cobordism distance. And similarly, I can define a quantity B, which is kind of the opposite. I do minus, take my slice-torus invariant, minus P plus 1, plus slice-torus invariant of K. And that will be a lower bound in the same way for the distance between this negative torus knot and K. Nothing has happened so far. I'm also gonna remind myself what squeezed nest means with this equality. And now I'm gonna write down a little calculation. If I look at the distance between these two torus knots, I know what this is. It's actually equal to the sum of their 4 genera that you get out of local Thom conjecture if you want, or even the existence of slice-torus invariants. And then you know that slice-torus invariants equal the 4 genus. So here you get this, and then here you have to switch signs because it's a negative torus knot. You get this. This is kind of by definition of slice-torus invariant. And now clearly, this is just A plus B, because in A and B, I have canceling phi of K. Okay, so far, so good. But now, by 1 and 2, I have that this is less than the distances in this funny little metric between my torus knots and K's. And now I want to use the fact that I'm squeezed. Squeeze means for big enough choice of P, I actually have that this is an equality. This is equal to this distance. But now all the sequence of inequalities that started here and ended here became an equality. So I now know this has to be an equality. And from this, I conclude my 1 and 2 are equalities. And that's the end of the proof, because if you go up here, you just had this inequality. This now becomes an equality. Over here, I have a quantity that doesn't depend on my slice-torus invariant. And over here, I have an exact number, namely the 4 genus, because it's a slice-torus invariant. So I have an expression for phi of K that doesn't depend on what slice-torus invariant I had. And so this proof is a very simple trick, but somehow it's very helpful, because if you had a homogeneous knot, did you know that the S invariant was equal to tau? And could you have given an explicit formula? With this, you can. And then maybe your favorite refinement of the Rasmussen S invariant also is equal. And a priori you didn't know. I think it's kind of a fun trick. Okay, but maybe too technical, too explicit. That's the end of the proof of this observation. And so I want to end on telling you a little bit about the proof of this theorem and how silly the proof actually is. I hope to convince you. Questions up until this point, or in particular? Yep.
No question. If you go back to slide, just so it seems like a lot is hidden. I mean, this is a slick observation, but a lot is hidden in maybe just the fact of being squeezed. Like, how hard is it to prove that all these things are squeezed? All these.
It's not that hard. Andrew is going to show you some pictures. It's, for example, the fact that alternating knots are squeezed. Maybe, I don't know, I think understanding that the figure 8 knot is squeezed is the first place, and it's just, you draw some cipher surfaces, you draw some cipher circles, you resolve some positive crossings to get to a negative knot, you resolve some negative crossings to get to a positive knot, you check that certain cobordisms are minimal. I hope Andrew will explain you. So I agree with you. So I'm making good publicity for Andrew's talk. Okay. If I were there, I would draw you a nice little surface on the blackboard. I think Andrew wanted to be there, but couldn't. If in the coffee break virtually, I can show you a picture that convinces you that it's somewhat explicit to see that these things are squeezed. But I kind of agree with you. If you just look at the definition of homogeneous or alternating, you might not see it. So I think our insight that I want to advertise is maybe not the definition and our proofs, but kind of seeing that all these knots satisfy the definition is maybe more the point than the proofs I give, because this proof is silly. I agree. Is that an answer that is somewhat satisfactory?
Perfect. Thank you.
Cool. Other questions? If not, we go to Hanbanach. Actually, by show of hands, who has in their knotty research ever used the Hanbanach theorem? Because I'm very happy. It's a silly argument, but I see Adam Levine shaking his head in disgust. So I'm very happy that this is his reaction. So here's my here's why we're proud of this and why I'm happy.
Not disgust. I was just impressed.
Okay. Okay. So here's what's going on, and that's gonna be the last piece I do. I have to move again to be able to write here. Okay, what do I want to do? I remind you on the right of what the theorem is I want to prove. So what do I need to do? I pick a knot. And I pick some real number that I want my yet to construct slice-torus invariant to have. So it has to be a number that is in this beautiful interval. And my job is I have to define a slice-torus invariant that takes this specific value. Here's what I do. I said something about a semi-norm earlier. Let's make this precise. If you take an abelian group, like in tensor with R, it turns out that the stable Forge induces a semi-norm on this vector space. And I'm actually, let me maybe denote the semi-norm by the usual norm symbol. And I'm going to put a lot of details under the rug. I'm going to pretend that elements in this vector space are essentially not times tensor 1. There are other elements. You might have to take some limits if you want to do the details. They're in the paper. I'm not gonna. This is just about the ideas. So my first step is I want to consider the subspace of torus knots or positive knots. I'm going with torus knots. Let me define the span of, I take torus knots. I do PQ tensor 1. So that's an element in this beautiful tensor product. And let me just pick two P bigger than 2, strictly bigger than Q, coprime. The advantage of my choice is this isn't just any subset, this is actually a basis. It's clearly, if I said span, it's clearly a real subvector space of my V. And now I claim there exists for sure a linear map on T to R linear, such that two things are true. I want first, for every element T, I want phi of T to be dominated by the seminorm, meaning the value is less than what the value of the seminorm is for all elements in the subspace. And furthermore, on my favorite Taurus knots, I want the value to be what it ought to be, namely P minus 1 times Q minus 1 halves. And I'm going to give you two reasons why this is true. The cheaper one is just essentially put phi equal to the Rasmussen invariant. If you know that the Rasmussen invariant exists, you can just check that the Rasmussen invariant induces the right linear map. But let me tell you, the cooler way to do it is to know that all these elements are actually linearly independent. And you can just, that's a result of even, I'm blanking, Litherland, yes, Litherland. And you can just use local Thom conjecture or use local Thom conjecture. So you know what the values on these Taurus knots have to be, and then you can just find a linear map that on these posit basis elements is the right thing, and you can check that actually for all other elements that are linear combinations, you still get this domination result. So you could use the Rasmussen S invariant or tau, but you don't have to. Just this map just exists. I'm not saying more, I'm just informing you. Here's my second step. So I've defined a slice-torus invariant on Taurus knots. That's not particularly impressive. Second step, I'm going to look at an element in my vector space that is K tensor 1. So I'm just, you know, I view a look at the where the knot goes if you try to map from your abelian group into this vector space. And here I'm going to make an assumption. There are two cases. I'm going to look at the more interesting case when you're not already in this subthing. Turns out if you are in this subvector space, then you were actually squeezed, and then this interval was very boring, and there was no choice, interesting choice to be had. So trust me, the more interesting case is when you're not already essentially a Taurus knot. Maybe that sounds believable. I'm going to define another subspace. Namely, I'm just going to take the subspace I had before, and I look at the span of V. Since the vector wasn't in there, now I have a nice little new vector space, and I'm just going to define a linear map. Linear map on W that goes to R, and I'm just going to say an element is of the form T plus some multiple of V, and I'm going to map this to, you guessed it, phi of T, because I already have a map defined on T, plus S times lambda, the value I want. Now comes the claim. The claim is this is actually dominated. So that means whenever you plug in an element out of V for your linear map, the norm bounds it for all elements in W. And now somewhere I have to use this, well, my definition and or my where lambda actually lives. And let me give you a formal reason. I feel like I started 3 minutes late, so I feel like I still have 3 minutes. Is that a fair assessment of things?
Yes.
Great. So let me simplify some further. Again, this is just to give you an idea. I'm going to assume that I have an element W that is of the form T plus V. I'm just assuming S is equal to 1. And more crucially, I'm just going to assume that my T element is secretly a positive Taurus knot. That's a somewhat crass assumption, but you know, that's a case we certainly have to treat. Maybe negative torus knots should also be treated, and then sums or differences of those should be treated. I'm just going to do this case. Okay, with that in place, I'm going to look at my linear function. What is it? Oh, on the things that are in T, I'm just the 4 genus, because my linear map is what it is. So I'm just 4 genus or stable 4 genus of T plus 1. That's what I'm on this element. What am I on the other element? By definition, lambda. Now comes the observation. I picked my lambda in this interval. So for sure, this is bounded above by P plus 1 plus L of K. But this L of K, I told you at one point, the L of K is the limit of a decreasing sequence of things which involve torus knots. And in particular, if I take the pth element, I see that I get now comes this pth element that was T, P plus 1, connect some K minus stable 4 genus of T, P plus 1. But practically enough, that's just the stable 4 genus of T, P plus 1, connect some K. But this is actually kind of by definition what the norm was of my element. So I have shown my claim, and I have convinced you there's a linear map defined here. And now you're done. Step 3. Apply Hahn-Banach. Extend L to a phi on the entire vector space. Linear such that you still have domination. Let's call this phi is less than the norm for all guys in here. And now you can define your slice-torus invariant as I start at knots. I have a map to the concordance group. I have a map to V. And then here I can put my phi, and this is to R. So this is your slice-torus invariant. Just out of, and the upshot in this proof is now done, is that I never even used a knot homology theory. So slice-torus invariants exists, and they exist with the values you want. That's the end of my thing. And I suggest that we, if you don't have questions at this point, that we switch to my list of questions, which are here. And yeah, let me actually stop here and just let this question sit here. And if you have questions about them, we discuss them in the question session. Thanks.
Okay, would anyone like to ask the question? Yeah, Melissa.
Seems like a very, oh, I think you can hear me. You can hear me, right?
Yeah, if you speak loud enough and slowly enough, sometimes there's a little bit of crackle. Also, hey, long time no see.
Yeah, hey. Is there an analog for like rational homology spheres and homology concordism group using the invariants or that kind of?
It's a very good question. It can't be the invariants, I think. And I don't know. I mean, one sub-project of the squeeze people is try to come up with analogs of squeezing and these type of invariants for 3 manifolds or certain special 3 manifolds under certain special cobordisms. And I have no answer for you, but I think it's an interesting question. I don't think there's an obvious candidate. Like, for example, the invariant is not additive enough, or it's not big enough to kind of. Or I mean, what would you want from your theory?
Personally, it would be cool if it were related by double branch cover. To
Exactly. But then you need a quantity, you know, even if you start with a PQ torus knot, then what you get, Brieskorn 2 PQ. So now you need a really big invariant for these things.
Yeah. Okay, thank you.
You're welcome.
Sam, come forward a little bit.
I'll come closer. Hey, Peter.
Hey, Sam, cool to see you.
So I guess my question was gonna have to do with your question too.
Oh, perfect. You're setting me up to keep talking. That's so kind.
Do you have like candidates for a counterexample, or do you think this is true?
I think it's true. Okay. So Sam is asking about question 2. I showed you earlier that if you're squeezed, then your slice-torus invariants all agree. My hope is that question 2 has a positive answer, and I actually hope, let me just use this as an excuse. Question 4, which looks more complicated. Question 4 is something like, oh, maybe this quantity that I defined with a limit, maybe you don't need a limit. Maybe there's an explicit P such that the quantity is just equal to this thing with the 4 genus, and maybe you don't even need the stable 4 genus. It's just if you add big enough Taurus knots, things become simple. And and if this is true, then question 2 and question 3 are true. So I would want to think about question 4. And now you're telling me, oh, but Peter, this is a little bit too much to hope. But let me just remind you, there are lots of knots which are just squeezed. For example, all alternating knots. And I kind of think of squeezedness as something much weaker than sliceness. And like deciding when is an alternating knot slice is really hard, or determining its 4 genus, it's really hard. But its squeezeness status is not hard to determine. They're just all squeezed. So somehow this, looking at distances to Taurus knots which are far, far away, I hope that things become much simpler. So my hope is actually that this is true. So I would dare to call this a conjecture, not just a question. And in particular, to turn it around, I don't have any suggestion for a counterexample. You can take, I mean, I think I once thought about the examples Chuck has for stable 4 genus equal to a half. And I think they are just squeezed. I think I once thought about this. So at least the first suggestion where you could go, knowing that the stable 4 genus is complicated, I don't think you get to use that. But otherwise, I don't have suggestions.
Cool,
And I don't know how I would detect it, because it's not that easy to obstruct squeezeness if you don't do it that way.
Other questions? Okay, well, let's thank Peter one more time and have a break for lunch.
Have a great lunch, guys. I'm going to go for dinner.
What was that?
I wish you a great lunch, and I'm going to go for dinner because that's how it works here.
A meal is appropriate to your time zone. And we reconvene at 2 o'clock Eastern Standard or Daylight Time? Whatever it is. And Red Me Live is at 2 o'clock. Awesome. Thanks.